Hello, let's talk about Chapter 5, Modeling Randomness. The main topics in the chapter: probability distributions. That's really the overarching topic of the chapter. Probability distributions, otherwise known as probability models. Discrete and continuous distributions, distinguishing between the two of them and working with the two of them. The idea that probability distributions have center and spread, much like the distribution of any variable in a data set. The idea of center and spread applies to probability distributions as well. And then some specific types of probability models. The major ones we're going to work with in homework: the Poisson distribution, binomial distributions, and normal distributions. So, maybe the basic definitions of the chapter. What is a random variable and what is a probability distribution? A random variable is a variable that takes different numeric values depending on the outcome of a random process. Contrast or compare this with the way we initially defined a variable in Chapter 1. And I'm peeking at the book. It said, variables, attributes that take different values for different individuals. So in a data set, you can have different variables, and a categorical variable could take values that were categories or colors or words. Rank or numeric or quantitative variables could take numeric values. Well, for a random variable, they're always going to take numeric values, and the main thing is a random variable means they're going to take these values as the result of a random process. So there's always an underlying random process that is determining what value the variable will take. Okay, a probability distribution. A probability distribution then is a model for random behavior that specifies two things. It has to specify the values that a random variable can take, and it has to give a method for determining what the probabilities for each value are. So let's look at some examples, a couple of them. In the first example, we start with a random process, and it says spin a roulette wheel. Okay, so that's the random process. Now a roulette wheel has, has a total of 38 slots that the ball can fall into. 18 are red, 18 are black, and 2 of them are green. Okay, so actually 38 different things can happen. Then we define a random variable. Instead of using a small letter x or y, for random variables we tend to use a big X, big Y, or some other large letter. So we define x to be the financial impact of betting $1 on red. Okay, now given that random process that underlies and the result of the random process determines what the value of x will be. It'll either be win $1 or lose $1. But one random process could be used to define lots of different random variables. If we had this be the financial impact of betting $1 on a particular slot on the roulette wheel, we'd have different kinds of results here. Okay, but in this case we're defining it to be the impact of betting $1 on red. Here's the probability distribution. It has to do two different things. It has to say what values the random variable can take, and it has to tell you how to figure out the probabilities. The values are win $1, positive 1, or lose $1, negative 1. And the probability of winning $1 is 18 red slots out of 38 equally likely slots. That's about 47.37%. The probability of losing $1, there are 20 non-red slots out of 38. About 52.63% of the time the gambler will lose $1. A couple of characteristics of a probability distribution. The probabilities for all of the events, if you added them together, you're going to get 1, right? Because 100% of the time you either win $1 or lose $1. Here's another example. The random process is measure a random U.S. mail. Now I got to make a quick note. In a lot of the homework, people will get confused because the problem begins by describing a random process. The first sentence might be spin a roulette wheel. But it doesn't mean that the directions are telling you to go get a roulette wheel and spin it. Or it'll say, measure a random US mail. Doesn't mean you're supposed to do that. Other homework might begin, it might say, flip a coin. Don't flip a coin, you know. Or it'll say, here's a table with a bunch of data, a two-way table with data from survey respondents. And it'll say, first sentence, choose one survey respondent at random. You're not supposed to get out your calculator and choose one at random, and you're not supposed to assume that one and only one was chosen once and for all. It's just telling you what the random process is, and then there's going to be a random variable that's going to come after that, okay? So, measure a random US mail. We're just thinking, okay, that's the random process. Just imagine you pick somebody at random and you measure them. Then there's this random variable y, which is generated by the result of that process, and y is the height of this guy in inches. Okay, so you're imagining this could happen over and over and over again, and it would generate these random heights. Here's the probability distribution. What values can y take? Well, in theory, any positive real number could be a height. Mainly for men, it's going to be between 60 and 80 inches or so, but maybe some extremely short or extremely tall individuals will be outside of that range. So basically positive real numbers. And then we have to tell how to find the probabilities, and this is kind of quirky. The probability that y will fall in a given range, and in the example here between 71.5 and 72.5 inches, is given by this shaded area. Okay, so you get a probability density curve, this normal bell-shaped curve. Underneath it there's a total area of 1. All of the area underneath here would be 1 or 100%. You go down here on the axis, you find 71.5 inches and 72.5 inches, and you shade an area between those values, and under the density curve you figure out the area of that shaded stuff, and that's the probability. Quirky way to find probability, but that's how it works. In this model you can see that theoretically the probability of having a randomly selected male be exactly 6 feet tall, 72.000000 inches tall, it's zeros forever. Well, there's infinitely many possibilities here, so in theory the probability of getting exactly 72 inches is 0. There'd be no area at all in a single vertical line. So in a continuous probability model, we're always thinking in terms of a range of values. So in effect, this is really the event. If you say, what's the probability that this guy is going to be 72 inches tall, going to be 6 feet tall to the nearest inch? And you go, okay, that means the probability that he's going to be between these numbers, and therefore we're going to round to 6 feet to the nearest inch. That's equal to this area. Okay, now x, the discrete random variable defined by the roulette winnings. This is a discrete random variable because it takes a finite number of values. Well, actually, probably a better way to say that would be it's a discrete random variable because it takes these two separated individual values, -1 or +1. Another discrete random variable would be the total number of goals scored in a hockey match. Well, in a hockey match you might have 0 goals, or 1 goal, or 2 goals, or 3 goals. Let's see, from your perspective, I should count in the other direction. 1, 2, 3, 4. There could be 12 goals, but maybe in some rare cases there'd be 13 or 14. There isn't really any absolute maximum, right? So in theory, a discrete random variable might even have an infinite number of possible outcomes. For hockey matches, I guess this would be, whole numbers. But they're separated, right? They're discrete values, not like you can't get 2.175 goals, just 2 goals or 3 goals. So this is a discrete random variable. You can only get -$1 or $1 in your winning. Since x is a dichotomous random variable, it has the simplest of all probability distributions, what's called a Bernoulli distribution, and the mean of this distribution can be calculated with the general formula for discrete distributions. Given a discrete distribution, you can find the mean of the distribution by taking the sum of the individual outcomes, individual values of the variable multiplied by their probability. So in this case it would be $1 times its probability, 0.4737, plus -$1 times its probability, and the result is negative 0.0526. The unit on here would be dollars. Can you interpret this result in context? I mean, what does it mean that the mean of this distribution is negative $0.0526? Basically, that means that in the long run, in many trials of betting $1 on roulette, the average outcome is going to be a loss of $0.0526, or a little bit, about a nickel, 5.26 cents every time. So in 100 trials of doing this bet, you might lose about $5.26, somewhere in that neighborhood. So it's kind of a long range, or expected, or expected value, or a long range weighted average of what the outcome will be. Y is a continuous random variable because it takes an infinite number of values on a continuum. This is back to the men's heights. The probability distribution of US men's heights follows a smooth, symmetric bell-shaped pattern called a normal probability distribution. Through many observations, we know that the approximate center and spread of this distribution are mean of 70 inches, there's the center, standard deviation of 3 inches. Many naturally occurring random variables follow this symmetric bell-shaped curve. If I've drawn this correctly and I go to the mean, that's the center, and if I add a standard deviation and subtract a standard deviation, 73 inches and 67 inches, and go straight up from those, these are the points of inflection on the curve. So that's the place where the concave down, or the frown part, turns into the smile part, concave up. So let's talk about working with Poisson binomial and normal distributions. The hard part, honestly, is figuring out which model to use in which situation. And I won't talk about that here, but you might look at the document I posted on Moodle that's called Choosing a Probability Distribution, or Choosing a Probability Model. That'll give you more examples of how to go about that. But here it says the number of, let's get back there. Here it says the number of phone calls received each minute at an office follows a Poisson distribution with a mean of 2.7. Very characteristic of a Poisson model here. Something is scattered in time or in space. Phone calls are scattered in time at an average rate of 2.7 per minute. So what's the probability that 5 calls will be received in a random minute or in the next minute? Go to the calculator, second distribution, DISTR I think it is, second distribution, and then find Poisson PDF. It means Poisson probability distribution function. You have to put in 2.7 to tell it which Poisson model. The Poisson model is just determined by its mean, so average number of calls per minute is 2.7, comma, what is the probability that I'm going to get 5? This is a discrete model. It gives you whole number of calls. You're not going to get 5.1 calls. You're not going to get 2.7 calls in a minute. That's just the average. And when you hit enter, the calculator says about 8% of the time. Of course, if you did that for what's the probability of 0 calls, 1 calls, 2 calls, 3 calls, 4 calls, 5 calls, they'd start to add up to something very close to 1. Here's another example. Let X be the number of times a gambler wins in 10 consecutive roulette bets on red. This is not the same random variable we looked at before with roulette, because we're actually spinning the roulette wheel 10 times. The number of times a gambler wins in 10 consecutive roulette bets. So there are 10 trials here. This is very characteristic of a binomial situation, a fixed number of trials. And X follows a binomial probability distribution with n trials, 10 trials rather, n equal 10. And the probability of success on each trial is 0.4737. The probability that's bet on red is going to win. What's the probability the gambler will win exactly 6 times? So binomial probabilities give you these probabilities of getting a certain number of successes in a fixed number of trials. Same menu on the calculator, binomial probability distribution. The syntax here is N, P, K. So N, the number of trials, P, the probability of success on one trial, and K, what's the specific value of the random variable I want to know about? What's the probability that I'm going to get 6? Calculator says 18.2%. I've got to do a second part to this, so I'll see you in a minute.